So let's get started. What did we discuss so far? We discussed so far. We have discussed charges. We consider symmetry generated by view, that is space-time translation. And we knew the Lorentz, which is made up of angular momentum and boost. And continuous symmetries mean conserved charges, and P mu and M mu are the conserved charges for symmetries under space-time translations and Lorentz translations. This is Lorentz translations. These we may call collectively as space-time symmetries or space-time charges. Symmetries, we have set charges, so space-time charges. And all of them are spin 1. And this is spin under the Lorentz group. E mu is a vector, spin 1, and mu is also spin 1. Does anybody know why mu is spin 1? The same reason we at some stage say if mu of electromagnetic field strength is spin 1, and any antisymmetric tensor with two indices is made of Lorentz representation 1, 0. The self-dual part is 1, 0, and the 0, 1 part is anti-self-dual. So each component has spin 1. We'll do this in more detail later. So the point is that all of them are spin 1 and they are bosonic. So let me call this set A, set B. In addition, we have electric charge. We have what let's call them non-space-time solutions. Non-space-time solutions. Or internal solutions. Like electrical charge. Q-electric. That's also conserved. Or you may have more complicated, non-obedient conserved charges. Internal conserved charges. Such as this SU2 left cross U1 of electroweak AD. So-called standard model. Of particle electroweak. Or, and for example, SU3 color of You see, they are all space-time. They are not space-time symmetries because all of them are spin zero with respect to space-time. Lorentz spin zero. All these charges have space-times spin and Lorentz spin. So that means they are unchanged under Lorentz constant. Now all the charges in A and B in this case are bosonic in this case. Or bosonic. That means they're anti-commuting. The parameters associated, the transmission parameters associated with them are, they're commuting or commuting. Generators have algebra, which has commutators, not anti-commutators. And the transmission parameters are made up from commuting variables. Not only that, that means these transform bosonic states or fields into bosonic fields, bosonic states or fields, and fermionic states or fields into fermionic states or fields. They don't change spin. Bosons stay bosons and then rotate them or transform them amongst themselves, bosons. Fermions stay fermions. Vector particles stay, vector fields stay vector fields. Various components can get mixed up, but they don't change spin. These do not change spin. Spin here means the Lorentz spin, space-time spin, not these internal spins of these kind of groups. Sometimes we use the same word, spin there. In fact, there is a theorem and theorem is due to two gentlemen, Coleman and Mandula. And the theorem states there can not be any conserved charges in nature with spin greater than 1. There's one thing missing, conserved bosonic charges. There cannot be any conserved bosonic charges greater than spin 1. So spin 0 and spin 1 examples we know already. For a long time, people tried to find symmetries which could mix spins. And that's the time when this theorem came and stopped all that enterprise. There's a huge enterprise going around. And this theorem stopped that, because then it conclusively proved that you cannot have symmetries which mix spins. But the weak link in this theorem was the word bosonic. Weak link in this no-go theorem is the word bosonic. So the question is, can there be fermionic or spinorial with spin, with spin 1/2, 3/2, 5/2, and so on, half integer spins. That's what spinorial representations are. Can there be fermionic or spinorial conserved charges in nature? And the answer to this question turns out to be yes. And the people who answered this were three gentlemen, Haag, and then some, what is his name, Loponsky or whatever, and Martin Sonius. And this is what we'll discuss today now. So we'll discuss conserved spinorial charges. And that's what supersymmetry is. So what do we do? Let's explore possible conserved charges in representation half zero under the Lorentz group. As a doublet under the first SU2 of Lorentz algebra and a singlet under the second SU2 order. And these objects we label the components. The two-component representation, we label the components with undotted Greek index alpha. But alpha takes values 1 and 2, because there are two components. But there can be more than one such charges. So I, 1, 2, 3, and let me say there are capital N charges. And if that be so, then there would also be conjugate charges in representation 0 half. Singlet under the first SU2 of the Lorentz algebra, doublet under the second SU2. And these objects we had decided in a notation, we'll call them bars and label the spinorial indices with dotted indices, 1 dot and 2 dot. And since these are n in number, so now, if they are conserved charges, they must satisfy an algebra. What is the possible algebra we can construct? First thing is we could ask the question, what is the commutator of Qi with Q bar now, because they are spinorial charges, they are anti-commuting charges. Instead of commutator, we'll have an anti-commutator. And we know how to raise and lower these dotted indices or undotted spinor indices through those epsilon symbols that we introduced. So now, we would like to see what is the possible structure of this anti-commutator. First, under Lorentz representation, what would this be transformed like? This transforms like half 0. This transforms like 0 half. So whatever this whole combination is, has to transform like this. So whatever we write on the right hand side should have the properties of transforming like this. At some stage, we had set up composition rules for representations of SU2. Let me remind you here. Composition rules for representations of SU2. So if I take a J1 representation of SU2 and compose it with J2, spin J1 and spin J2 representation, then it is a reducible representation which can be written in terms of irreducible pieces as mod J1 minus J2 spin plus mod J1 minus J2 plus 1 spin representation, and keep increasing by units of 1 till you reach the value J1 plus J2. That was the composition rule. So here what do we have? I have spin half multiplied by a singlet. Well, spin half multiplied by a singlet is spin half. That's not, because singlet doesn't change the nature of spinorial nature of this representation by multiplying by singlet. Now, but if on the other hand, if I had product of two spin half representations of this SU2, I would have, I can decompose it in terms of irreducible representations in terms of a singlet plus a triplet. Just applying this rule, the standard angular momentum composition rule. So this is a two-dimensional representation. This is a two-dimensional representation. Singlet is a one-dimensional representation. Triplet is a three-dimensional representation. So these have two independent complex components, There's one component in singlet, 1 in, a 3 in triplet. Same way, if I took spin 1 representation and composed it with spin half, that gives me spin half plus spin 3 half. Again, in terms of independent components, this has 3, this has 2, this has 2, and this has 4. And similarly, you can construct more complicated product rules. So anyway, here in this context, we have a simple trivial rule. Half times spin 0 is half. 0 times spin half is half. So if these are conserved charges, spin half conserved charges, then the commutator of these two also has to be a conserved charge, and these are fermionic, spin fermionic, product of two fermionic objects is bosonic. So do I have a bosonic conserved charge in nature in this representation, Lorentz group representation? We have already said that this is spin 1 representation. Total spin is half plus half. And we already have said P mu. Let me write the components of P in this 2 cross 2 matrix. P0, P3, P1, I, P2, P1 plus I, P2, P0 minus P3. Break the 4 components of P mu into a 2 cross 2 matrix. P0, P3 plus P3, P1 minus I, P2, P1 plus I, P2, P0. This is nothing but sigma mu alpha alpha dot with P mu, because so a 4 vector P mu can be seen as a 2 cross 2 matrix in the spinorial basis, alpha dot alpha basis. And this is the one that transforms as half representation of Lorentz group. Half under the first SU2, that is this first alpha index, half under the second SU2 of Lorentz algebra, that is the alpha dot index here. So therefore, I can write Q alpha I, Q bar alpha dot J anti-commutator to be proportional to this. So sigma mu P mu alpha dot alpha. And since I and J, I have thought of I, 1, 2, 3 are independent n fermionic charges, and their conjugates are here. And then we put a factor 2 here for convenience, so that the algebra later becomes simpler. That's just a normalization. Is that clear? Now, after having studied a possible structure of the algebra for spin half conserved charges, I could ask the question now, are there any spin 3 half conserved charges? So, for charges, so let's call them Q in 3 half 0 representation and conjugate charges Q bar in 0 3 by 2 representation. I am not putting indices and kinds of things on that because I will not need it, because I'll soon argue out that such charges don't exist. So I don't need no detailed structure. So what do I have? I have to study again for the same commutator of properties of this commutator. Under Lorentz group, it will transform as 3 half 0 cross 0 3 half. And which, according to the is that spin 3 half times spin 3 half, spin 3 half times as spin 0 is a spin 3 half representation of SU2. And spin 0 times spin 3 half is a spin 3 half representation. So this commutator transforms under Lorentz group as a bosonic charge, because this is a real representation. When the entries are same, is a self-conjugate representation. It's a bosonic charge of total spin 3 half plus 3 half, 3. Total spin is 3. But when we said there is Mandula-Coleman theorem that tells us there are no bosonic charges with spin greater than 1. So, Coleman, Mandula theorem does not allow for any bosonic conserved charge with spin 3. So therefore, we cannot have in nature by this argument a spin 3 half conserved charge, because such an algebra cannot be made. Your question?
Why? What is the problem?
If you write a field theory with them, with the properties of relativistic or quantum field theories, they are not consistent. Quantum field theories. That is a theorem. I don't want to discuss it here. That's too into detail. But I can now show you how that theorem proof is there.
Something goes wrong.
Is that the theory is not self-consistent. Consistent. You cannot build up a consistent theory with high conserved charges. Okay. So that tells us that you cannot have spin 3 half conserved charges. Similar argument will hold for charges in representation of 5 half or 0 5 half or 7 half and 0 7 half and so on and so forth. So far, the only possible conserved charge that we have is the one with spin half. Fine. But anyway, we have not fixed the algebra completely for spin half. See, we have fixed one part of the algebra. There would be other pieces of this algebra. Let's try to fix that.
So in particular, let's try to evaluate, let's study the anti-commutator Q alpha I Q beta J. Take two Q alphas in spin half zero representation and half zero representation. What can be this anti-commutator? What can it be? Now again, this transforms as half zero cross half zero under Lorentz transformations. And by composition rules, half and half, this is 0 and 0 plus 1 and 0. This is a singlet under Lorentz transformation. This is spin 1 under Lorentz transformation. Now we said earlier now do we know, so this has to be some scalar charge. Now spin 1 0, do we know any conserved charge in spin 1 0 representation? Self-dual part of m mu nu is in 1 0 representation. What do we mean by self-dual? Let me write it here. M mu nu, self-dual and anti-self-dual. Plus is self-dual and minus anti-self-dual is half m mu nu plus minus 1 by 2I epsilon mu nu lambda rho. That is the definition of self-dual and anti-self-dual. So this is self, anti-self dual. I think I had put I upstairs in some of my earlier things, but I is really downstairs here. So if correct that, if that's what is in the notes. And this is with the choice where epsilon mu nu lambda rho are completely antisymmetric. And if you interchange any pair of indices if you interchange a pair of indices, it changes sign. And if any pair of indices is equal, it is 0. With the normalization 0, 1, 2, 3 as plus 1, and that is same as minus 0, 1, 2, 3 down. Recall, we had said that sigma mu nu, these matrices sigma mu nu that we had constructed, which was half I by 2 sigma mu sigma bar nu minus sigma nu sigma bar mu and sigma bar mu nu as I by 2 sigma bar mu sigma nu minus sigma nu bar sigma mu, where sigma mu, but 4 2 cross 2 matrices, sigma 0 as 1 and sigma 1 2 3 as 3 poly matrices. and sigma bar mu was 1, and sigma 1, 2, 3 as minus times the Pauli matrices. This is how we had defined, and then we had also claimed that sigma mu nu is self-dual. That is, sigma mu nu is same as 1 by 2i epsilon mu nu lambda rho sigma lambda rho. And sigma bar mu nu is anti-self-dual. That is, sigma bar mu nu is minus 1 by 2i epsilon mu nu lambda rho sigma lambda rho bar. Did any of you check these identities? No. So, yeah, he has done that. First one, yeah. The second one is follows. Anybody else? You did it? Okay. So now, sigma mu nus are self-dual, sigma mu nu bars are anti-self-dual. So if I multiply sigma mu nu with m mu nu, since this is self-dual, it will project out the self-dual part of m mu nu. Since this is equal to that, I can add them up and divide by half. This is equal to that. So I write this plus this, equal of objects divided by half. That is the same as this. Now take sigma mu nu out. Now in this object, change indices mu nu, interchange mu nu and lambda rho pair, and remember if you interchange a pair of indices here is the same object. I can write this as 1 by 2i epsilon mu nu lambda rho m lambda rho. And that is sigma mu nu times m mu nu plus. So sigma mu nu, m mu nu has only the self-dual part of m mu nu. And therefore, 1 by 4 sigma mu nu alpha beta m mu nu transforms as half-zero representation by construction. Because under spinor transformation, the free indices are alpha and beta. This is half representation, and this is half representation. Half times half is 0 plus 1. But these are traceless objects. It has no zero component. Therefore, it has only spin 1 component. Clear? Now this object, using the definitions there, show that sigma 0 I, let me see, have I written down, if you calculate is I times Pauli matrices sigma, minus I times Pauli matrices sigma. Sigma ij is epsilon I j k sigma k. Put that in here and show that this object is nothing but JL plus I KL sigma L by 2. Do this bit of algebra and show that this is what it is, alpha, beta, the matrix components. Now, J plus IKL was the generator of the first SU2, right? What we call ML. And that's a triplet that lives under as a triplet representations of that SU2. That is spin 1 representative SU2. So you explicitly see this way. These are the generators of. Have you written sometimes SU2 gauge fields in standard model in matrix formulation in terms of a gauge field times the generator of internal SU2 transformation? This is that way of writing it. Instead of gauge fields, we have here ML here. Okay. So this makes it clearly transparent that this is 1, 0. Even this makes it that it's 1, 0. So now this discussion tells us that this commutator, let me write again, anti-commutator can be a Lorentz scalar plus 1 by 4 sigma mu nu alpha beta m mu nu. Some constant, you can just put a constant here, times some constant that we don't know, C. Now, algebra of generators of conserved charges or symmetry transformations, in addition to having the algebra, the generators are also expected to follow another property, which is the Jacobi identity for the generators. So these charges not only do have to have the algebra, but they must also satisfy the Jacobi identity. What is the Jacobi identity? Jacobi identity for 3 generators is commutator of X with commutator of YZ plus commutator of Y, ZX commutator of Z with XY is 0. This is for bosonic charges. If you have fermionic charges, commutators will become anti-commutators. So if Y and Z were fermionic, then instead of commutator here, you would have anti-commutator. And the bracket between a bosonic and a fermionic charge is always an anti-commutator. Sorry, is always a commutator. Between 2 fermionic charges, it is an anti-commutator. Between 2 bosonic charges, it is a commutator. Between a bosonic and a fermionic charge, it's also again a commutator. So you use those rules. So you will have a whole set of, say for example here, if I had boson anti-commuting Q1, 1 charge, and Q2 and Q3, this would be an anti-commutator, but this between these two, it would be a commutator. Plus Q2, Q3, Q1 Is there a change of sign there? No. Q3, Q1, Q2. So you would have Jacobi identities of this kind. Sometimes you may need to change if there are mixed ones, Bose and Fermis. Okay, some generators could be bosons, some generators could be fermions in a symmetry. One of them could be M mu, other could be P and two Qs. Then you have to worry about, in writing these kinds of things, there may be a change of signs depending upon how many times a spinor charge has been commuted across. So that's a matter of little detail. But the statement is that if I insist on Jacobi identity, which is what I should, then let me go here. Does not allow 1-0 charge in the right hand side of that commutator, which means this coefficient C that I have here has to be 0 in order that the Jacobian identity is satisfied. So that leaves me that the possible piece for this algebra, Q alpha and Q alpha, on the right hand side is only a Lorentz singlet. Now, is there an object with two spinorial indices alpha and beta which transforms like a singlet under Lorentz group? In last lecture, I think we made some bit of fuss about such an object. We showed that an object with two spinorial indices alpha and beta that does not transform under Lorentz transformations, which means a singlet in Lorentz transformation, is epsilon alpha beta. This is the one that we use to raise and lower, right? For the reason because it does not change under Lorentz transformations. It's a two-indexed object, but does not change under Lorentz transformation. So therefore, this has to be proportional to this. But this is antisymmetric in alpha beta. This object is symmetric under the simultaneous change of alpha beta and I and j. So it should also be proportional to something, let me call it Z ij, where Z ij is antisymmetric under interchange of I and j. Is that clear? In order to be a singlet of SU2 with tensorial labels, spinorial labels, alpha beta, it has to be proportional to epsilon alpha beta, because that's the only two-indexed spinorial object we know that is Lorentz invariant. But this whole combination is symmetric under simultaneous interchange of alpha beta and ij. So therefore, it has to be multiplied by some objects which is antisymmetric under interchange of ij. And this is also Lorentz scalar. And then we put some factors 2√2 here for convenience. So that is Now I could now do the similar discussion for conjugate charges. And this object transforms under Lorentz transformation as 0 half times 0 half, and that is 0 0 plus 0 1. Now for this object, I could take a 1 by 4 sigma bar mu nu alpha dot beta, or alpha dot beta dot times m mu, because sigma bar mu nu is anti-self dual. This will pick up an anti-self dual part of it, and this transforms under Lorentz transformation exactly like 0 1. And if you wrote down in terms of generators, it is JL minus IKL sigma L by 2 alpha dot beta dot. You recognize this as the N generator for the second SU2. So this transforms under the second SU2 of the Lorentz algebra as a triplet, and that's what spin 1 is. But again, for same argument, Jacobi identity does not allow this. And therefore, so finally, it has to transform only like an SU2 singlet, a Lorentz singlet with two indices alpha dot and beta dot, that's an epsilon, and you multiply with Z, where Z bar has the property it's antisymmetric under interchange of I and J. So what have we done? That in order to have supersymmetry algebra, or for these generators, this and this, we need an additional set of charges, Zs, because if this is conserved, Z should also be conserved. And they are charges which are Lorentz singlets, scalars. So Z and Z bar are scalar charges, also called central charges. Central charge is the property that I must also prescribe the algebra of these Z's with Q's. Z's commute with Q's. Z's commute with every other symmetry of the theory. So that's what a central charge is. Z's commute with any other charge of the algebra. So whenever you come across such kinds of conserved charges, they are given a name called central charge. That's a name. What it describes is that they commute with all the other charges in a given algebra. Also notice for Zij to exist, we need at least n, we need n at least 2 or greater. N is the number of total charges. I, 1, 2, 3, 4, n. The total number of such charges, if it is 1, which means I has only one value, with one value you cannot put anything antisymmetric in 1 and 1, right? So Z will have to be 0. For n equal to 1 supersymmetry, which means with 1 half 0 supersymmetric charge and 0 half conjugate charge, only 1 each, there is 0 on the right hand side. N equal to 1 supersymmetry charge algebra does not have any central charge. Is that clear? In order to have central charge, you must have at least n equal to 2. Then you can put here 1 and 2 and 1 and 2, that would be 1 non-zero central charge. Clear? Now let's try to fix the properties of these charges with other conserved charges of nature that we know. This is not cleaning up. So now next fix the commutator P mu with Q alpha I. Now this will be a commutator because this is one bosonic charge, one spinel charge. So you'll have a commutator between them. Now we use the same trick, study its Lorentz transformation properties. P mu is in half comma half representation and Q alphas are in half zero representation. What can that be now? This, by the rules that we still have there, half and half is 0, half plus 1, 0. Is that right? 1 half, something is not right. 1 half, right? Now, there can be no spin 3/2 conserved charge in representation 1/2. So the only possibility we have, so this is not allowed. This. So what does it mean? So it could be P mu Q alpha I, and half zero, what do we have? Q itself. So you can have Q on the right hand side. No, something is not right. Q bar. So let me, Q bar. So call this beta I. It's multiplied by something, call it C mu, with indices alpha, beta dot. That's what it can be. A Q bar, so beta bar up times C mu. C mu's could be some set of sigma mu news or some whatever it is. So some sigma mu news, some sigmas. In fact, some sigma, it's some constant times sigma mu. Again, Jacobi identities do not allow this possibility. That means if you try to satisfy Jacobi identities, you'll see sigma, C mu 0. And that gives us and similarly okay. Next, let's try to fix the commutator of Q alpha I with M mu nu Lorentz generators. And use the same argument. This is half zero. This is the self-dual part is 1, 0, and anti-self-dual part is 0, 1. M mu nu, we had the discussion which we rubbed off, is made of self-dual part and anti-self-dual part. So M mu nu is a reducible representation. The self-dual part lives in 1, 0, and anti-self-dual part lives in 0, 1. And let's do this algebra now. Half 0 cross 1, 0 is half 0 plus 1, 0. And half 0 cross 0, 1 is 1. 0, 1 is half 1. Is that right? Something is not right? Oh, this is 3 by, sorry, 2. Right. Now, this is not allowed because this is spin 3 half conserved charge. This is not allowed, spin 3 half conserved charge. That leaves only this one. So commutator of Q alpha I with Lorentz generators M mu nu can be only a spin half zero representation. So spin half zero representation is Q itself multiplied by some C mu nu alpha beta. The C mu nu is unknown coefficients. Now I've used Jacobi identity again. That tells you that C mu nu alpha beta is exactly half sigma mu nu alpha beta. That's why I wrote that. So Q alpha I M mu nu is half sigma mu nu alpha beta Q beta I. Similarly, Q alpha bar alpha dot I M mu nu is half sigma mu nu bar alpha dot beta dot Q beta dot I. Same kind of an argument will tell you that. Is it clear? But that's not a surprising result. Why it's not a surprising result? Not a surprising result. Because what does this state? This only states that Q alpha under Lorentz transformation transforms like a half zero representation, and half zero like half zero representation, and generators of half zero representations are precisely half sigma mu nu, right? Because generators of half zero representation and generators of zero half representation this is what we discussed last time. The generators of transformations on upper two components of Dirac spinner, which transforms at half zero, and lower two components which transform at 0 and half, are respectively half sigma mu nu and half sigma bar mu nu. So this is that result. So this is not surprising. I think with this we have completed the construction of the supersymmetric algebra. Let me summarize it in one place. So summary. We can have only spin half conserved charges. Only spin-orbital charges are spin half. They cannot be high spin. That's one statement. And those spin half charges have the algebra Q alpha I, Q bar alpha dot j anti-commutator is twice delta I j sigma mu E mu alpha. Let me put it down, alpha dot here, alpha dot. And for q alpha I, q beta j anti-commutator is 2 root 2 epsilon alpha beta z I j. And q bar alpha dot I, q bar beta dot j anti-commutator is 2 root 2 epsilon alpha dot beta dot z bar I j. P mu q alpha I commutator is 0, P mu bar is 0, and then q alpha I commutator m mu nu is half sigma mu nu alpha beta first, second index q beta I, and q alpha dot I m mu nu is half sigma mu nu bar, first index alpha dot, second index beta dot I. This is the complete algebra. And then it has introduced for n greater than 2. Now I is 1, 2, 3. So this is n equal to n supersymmetric algebra. For n equal to 2 or larger, there is a possibility of central charges z's. And z's commute with all the generators. I'm not listing them. Now, since we have n supersymmetric charges, Qi's, I could rotate them amongst themselves. So I have the charges Q alpha I equal to 1, 2, 3, and n. I could rotate them amongst themselves, Qi is, by multiplying by a matrix Uij, Q alpha j. Right, that will mix these nu charges, and they are complex charges. I can rotate them through matrix U, which is unitary. That means U dagger, U is 1, identity. So n cross n, unity matrices. So rotate means call this prime, right? The new charge. Rotate these n charges by a unitary transformation. Transform them by unitary transformation. And U, I could write as exponential I, transformation parameter Zi times generators of this transformation. Zi's, I's are generators of Un with an algebra, and A takes values 1, 2, 3. Can anybody tell me how many generators are there for Un? transmissions, n square, simple enough. For SUN, n square minus 1, and for UN, n square. So there are n of them, and they satisfy an algebra of their own. I think there is an I somewhere, right? Where these ABCs are coefficient, some constants, they are called structure constants. Similarly, q bar alpha dot I would transform as q bar alpha dot L U L I dagger. The conjugate charges. Q transforms like this, conjugate, this is conjugate of that, will transform like that. Now, under this such transformation, this algebra is not changed. That is, the algebra of the transforms generators. Stays the same. Is that clear? Take this, multiply by u here and a u here. Two u's. Multiplying I index here, j index here. I and j are same. That is u dagger. Multiply u and u dagger here. That is u dagger product. That's one. Clear? Now, central charges have these indices ij's, so they transform. Means they get rid amongst themselves. And others are trivially true. what does this transformation rule tell us? Q alpha I prime is Uij n cross n matrix. It tells us that Q alphas form a defining n-dimensional representation of group Un. And therefore, Q alpha I, the commutator of Q alpha with this group generators, Un generators, is simply the representation matrices n cross n representation matrices of the n-dimensional representation of Un, and they are Hermitian. T A Hermitian is K. Because this transformation property tells us that they transform like the defining representation, n-dimensional defining. They have n components, n-dimensional defining representation. And this tells us the commutator of this generator has to be the matrix representation in the n-dimensional representation. And for conjugates, these transform as conjugate n-dimensional representation. This as an n and this as an n bar. So that is what the algebra of supersymmetric algebra with the internal generators, the Un generators, which rotate the n charges amongst themselves. Simple example. I'll take 5 more minutes. Time is over, but I'll take 5 more minutes. Today we start a little late so that we can close this discussion. Simple example. N equal to 1. This group Un of internal symmetries that rotate the Q charges is now 1, n is equal to 1. So U1. Internal symmetry group is U1. There's a name given to it sometimes, it's called R symmetry. What does it do? It's a rotation of phase. Q alpha I transforms to rotation by phase. Q alpha I, Q alpha bar I. I is only 1, so I is only 1. So it's the group of rotations of fermionic charges by phases. This one rotates by phase and this one rotates by its conjugate phase. In other words, the R charge or this U1 charge for this object Q is +1, for this one is -1. So if I write Q R commutator, if R I call the generator of this U1 charge, this commutator is Q alpha, and Q bar alpha dot R is minus. Is it clear? So what does that mean? Now Q alpha lives in the representation of the first SU2 of Lorentz group. Q bar lives in the second representation, in the second SU2. First, fermions that live in the first representations of SU2, we said they are the left-handed fermions. That live on the second SU2 are the right-handed fermions. So the R charge of the left-handed objects is +1, R charge of right-handed objects is -1. What does that mean? This charge distinguishes the chirality. So this is a chiral charge. Or axial charge, chiral charge. It distinguishes left-handed chirality and the right-handed chirality. So the last remark of the day. See, last time we discussed representation theory of Poincare group. Poincare group was generated by P mu and M mu, and we gave the algebra for them. Now, if to this Poincare group add supercharges, Q alphas and Q bar alphas, and that is a algebra that we discussed, and give it a name, that gives us super Poincare. Algebra of the charges. When we discussed the representations of Poincare group, we said the representation of Poincare group are given by two assignments. One was the eigenvalues of P square, the energy. Other was the eigenvalues of W square, which measured essentially the spin. Then we made a distinction between massless and massive things and discussed how they are described. Now, how do I describe representations of super Poincare? See, representation of Poincare group never change spins, but supersymmetric charges change spin. They change bosons into fermions, fermions into bosons. So therefore, spin, which was measured by W square, right there, eigenvalues of W square, cannot be a Casimir of super Poincare. So W square is not a Casimir of super Poincare algebra. That means, in fact, Q alpha commutator W square does not commute. W square commutes with P mu and mu nu, but does not commute with Q. So does not commute. Exercise. We are given the algebra of how P is defined in terms of, W is defined in terms of P mu nus and P mu's and mu nus. Use that algebra to show that this is not zero. So therefore, you cannot use W square to list the representations of super Poincare. But P square still commutes with all generators. So P square is still a Casimir of the super Poincare. So therefore, a super multiplet has a common mass, means all members have the same mass describes them, which is the eigenvalue, mass square is the eigenvalue of P square, but different spins. That means W squared does not leave them unchanged. Is it okay? I mean, with this we'll stop.